Yeah, I know it's a lot of information to take in, but we're going to progress to the next level. The example that's been given to you so far kind of assumes that we know these values. We know how many qualities a drug will generate, so we know how much it costs. You've made some rudimentary calculations in terms of multiplying quality of life against time to generate those qualities. But the reality is the evidence presented will come from a clinical trial that might compare X versus Y, whereas the actual drug used in practice is Z. So we'll need to make some kind of judgment and an indirect comparison, arguably, of X versus Z, if that's the one of interest. And that's where modelling comes into it. It's an unavoidable fact of life, unfortunately, and that was the title of a paper presented by an eminent health economist, Martin Buxton, going back over 20 years now, that it's something that just is part and parcel of making the evidence available to inform decisions on cost effectiveness. And there's several reasons why modelling is essential. And I'll go through these and we'll illustrate it with an example followed by a quick exercise afterwards before lunch. The first main application of modelling is to extrapolate data beyond the available trial follow-up period. It's very common to see this in cancer studies whereby there may be data from a clinical trial up to about median survival. So you've got 50% of people within that trial still remaining alive, 50% having died. But then the expectation is that treatments may continue for the other 50% for another period of time. So we can't just simply ignore and truncate the analysis at that point of median survival. We have to do some analysis to extend beyond that and try to extrapolate those survival curves until effectively the whole cohort has passed away, so that you can calculate their overall lifetime qualities and overall lifetime costs. There are several uncertainties involved in this type of work, obviously, because we don't know anything really beyond the trial time horizon. But nevertheless, if we were to ignore the issue of what happens after the 2 years, then that would lead to critical biases in our estimates of cost effectiveness. So it's a trade-off between precision and accuracy. On the one hand, we simply don't know what happens, but if we just assume nothing happens, then that introduces a whole load of bias that will affect our judgments on the cost effectiveness of treatments. A second application is to synthesize data from all relevant sources to best reflect the setting and perspective of the economic evaluation. It's very rare that all the evidence can be contained and collected within a single clinical trial. It's often the case that the trial would have key efficacy parameters, but nothing about quality of life, no utility EQ5D measurements, and certainly no resource use or cost measurement. So in order to bring those data together, you need some kind of a mathematical framework that allows you to be explicit in presenting the assumptions made and in accumulating the evidence together. A third example, and this is more commonly used nowadays for NICE appraisals, is to synthesize indirect comparisons when no such direct comparisons have been made. And as I illustrated in the example just a moment ago, it's often the case that you might have a trial comparing A versus B, but the real comparator of interest is C. And so how does A compare with C? Well, if you have other data comparing B with C, then you can triangulate the data and come up with some idea as the relative difference in effectiveness between A and C. And this is all called indirect meta-analysis, mixed treatment meta-analysis. There's different phrases for these, but it's an example whereby you systematically review all the evidence in relation to A, B, and C, identify all the clinical trials which are relevant to making the three-way comparison, and then mathematically or statistically pooling the evidence together and making judgments as to the relative effect of those treatments which inform the decision problem. A fourth potential application of modelling is to link intermediate outcomes with long-term outcomes. And so, for instance, many trials in diabetes may have HbA1c as an outcome, though that in itself doesn't measure quality of life or survival. It can be used to predict both, and there are several studies which have accumulated the evidence on the relationship between HbA1c and health outcomes. And so the modelling would synthesize and bring together those bits of the jigsaw in order to try and project the expected impact of changes in HbA1c with health outcomes to inform quality calculations. And finally, to predict the outcomes of the intervention. Now, this is a tricky one, but it's sometimes the case, certainly in recent times, whereby new medicines are given approval, conditional approval, without full maturity of the evidence. And so it puts the NHS in a very hard position whereby it could allow for market access and allow reimbursement, conditional on more data being acquired by the company in terms of further clinical trials. But at the point of making the decision, we still need the best guess estimate as to how effective the treatment is in order to try and make some estimation of the cost effectiveness. And so there are some modelling techniques which are applicable in that context. There are various tools, various methods which are available. I will just go through one or two superficially, but then there's a Markov model, which is a very commonly used one, which will be subject of an exercise in a moment. So a very simple decision model would be represented by branches of a decision tree. So, for instance, the one I use for my undergraduate teaching is the decision as to whether to carry an umbrella. It's either a yes or a no. There can't be any other decision to it. And it's conditional on the probability of the weather forecast suggesting that it might rain. So if there were a 20% chance of it raining and I were to carry an umbrella, then, and it didn't rain as a consequence, well, it's not as a consequence of carrying an umbrella, but it just didn't, it turned out that it didn't rain, I would have both the inconvenience of carrying an umbrella, but the joy of having no rain. So I might have a utility value, let's say, of about 0.8, because the inconvenience of carrying an umbrella, isn't that great. However, if it rained and I had an umbrella, well, that's fine. But raining is a bit miserable, so maybe I'd value it as 0.7. Now, if I didn't carry an umbrella and it didn't rain, that's a win-win, so I'd value that as a 1. And conversely, if I didn't carry an umbrella, but it rained, that's just miserable. And I'd value it probably worse than death. Okay. And you could see quite easily that that's a decision tree. You've got 4 branches. There's a probability to each of those events occurring, and there's a utility attached with the outcome. And if you multiply each value out by one another, you can work out on average, with a 20% chance of it raining, it's probably not worth my while to take an umbrella. So that would inform my decision. And that's the type of decision analytic approach used in straightforward, simple examples whereby, it's drug A versus drug B with some kind of a short-term health outcome, maybe for an acute condition. There may be a probability of one being effective, the probability of an adverse drug reaction occurring. There'd be costs and utilities associated with those outcomes, and it would allow you to decide whether one treatment is better than the other from a cost-effectiveness perspective. So then this slide just simply summarises that there are probabilities associated with these events. The proportion of patients calculated by multiplying the probabilities along these branches, and then that allows you to calculate the average or the expected costs and outcomes for each decision option. So that's a useful tool. It isn't used extensively nowadays, but there is a place for it for some health technologies. Another modelling method is called discrete event simulation, which I won't go into in any detail. It's just there for you to have in your notes. But it's based on the occurrence of an event, often used in modelling cardiovascular disease, whereby a patient may have a stroke, for instance, and that would then lead to a revised probability of some other event occurring in future years. For people who didn't experience a stroke, then their probability would be different in future years. So you can model individual probabilities of events occurring. So it's there just for you to have in your notes if you wish to read any further around that. Going back to decision trees, there are some pros and cons. The strengths or the benefits of using decision trees is that they are very transparent, they are very intuitive, and they are very informative for these types of one-off decisions that concern acute care problems. It does get more complicated when the time horizon is lengthier in terms of trying to work out the probability of things happening once something else has happened, etc., etc. They are used often in diseases which don't have any form of disease progression or any form of relapsing remission type conditions. They're not amenable to model those types of diseases. Often used for diagnostic tests where you have, a probability of testing positive or negative, and then what's the consequence of a diagnostic test result. So there is a place for them, but the weaknesses are that they do not account for time explicitly. So we don't know how to, when you see decision tree, you don't know what the actual time horizon is. The assumption is that it's all instantaneous, but you can factor in a time dimension to it. So it's not great when things occur over time. Patients can only flow in one direction. So I can't, for instance, in my umbrella example, then go outside and decide, well, maybe I'll go back in and leave my umbrella and then go back out again, because that's a sort of a reverse direction. So it doesn't really handle those types of events very well. And you can, in patients who respond well to treatment, but then may have a further episode later on the line, they're quite limited in the flexibility to account for those. If you want to extrapolate beyond the time horizon of a clinical trial, probably not well suited. And then I've already mentioned that time horizon becomes a complicating issue. So that's a preamble to using Markov models, which is a very frequently used method of economic modelling to synthesize evidence and to project over time. And I've got some slides which provide some examples of what is a Markov model and how can they be used in practice. It's a technique used for analysing repeated events. In other words, if a disease, a chronic disease, has associated with it people transiting from one health state to another, so it may be an HIV instance. It's some study I was working on recently whereby patients would be categorised in different health states, maybe dependent on their viral load, and they would improve as they had treatment. They would progress to a worse health state if they were non-adherent to treatment, or if resistance were to develop. And so those different health states, people can move from one to the other. This hypothetical cohort can transit from these various different health states and accumulate costs and QALYs as they do so. And so in order to conduct a Markov model, we need to define the disease into discrete categories, discrete health states. And a common example in cancer is people who receive treatment up until the point that they progress. And once the disease has progressed, then the third final state is death. So you'd have your three health states in a very simple model, and people would transit from one health state to the other as the condition deteriorates and as the disease spreads. In the starting health state, there would be a quality of life. So they would clearly have cancer, they would receive the treatment, there would be some cost of care, a typical cost of care of 1 month in that health state. But all that would probably be would be better in terms of quality of life than a progressed disease state, but maybe cheaper. Sorry, maybe more expensive, because that's the intense period when treatment would be used. Once you've progressed, treatment is often changed or discontinued, and that health state might be cheaper from a treatment cost perspective. And so a Markov model allows you to model that kind of sequence of patients as they move along their disease pathway. So a Markov model is run over a series of cycles. You would define your cycle length by some clinically relevant period. We have another study which is in motor neurons disease, and we've defined a cycle length that's been 6 months. Because over that period, the costs and how people remain in a health state are rather stable. So there's no real point in going to a shorter period. And besides, the clinical trials report their data after 6 months. That's why it all kind of marries up into defining a 6-month cycle. And then at the end of that cycle, if you had 100 people entering at that point, at the end of it, maybe only 60 would remain in that health state because the other 40 would have progressed to some other health state. And that progression rate would be dependent on the transition probabilities. And after each cycle, you can add up the costs and add up the QALYs. And over a lifetime, when everybody's transited to the death state, you can tot up all their costs and all their QALYs in order to calculate the total cost and total QALYs, which was the starting point of the previous exercise. Okay? Now, this is a representation of a Markov model structure, a simple 3-state model whereby patients enter the model in this asymptomatic disease state, where they would receive treatment, but there would be a probability for them after the first month to progress to a more aggressive disease state, the progressive disease health state as illustrated in the middle there, and there would be some probability of them dying from both the asymptomatic disease state and presumably a higher probability of dying from the progressive disease state. So that simple model can be defined by 3 probabilities representing the chance of progressing, the chance of the disease progressing, chance of death from the asymptomatic disease state, and chance of death from the progressive disease state. The other arrows can be calculated from those 3 probabilities, so they would be derived from the data available in those 3 probabilities. And this is how you would do that. So the probability of you remaining in the asymptomatic disease state after the first cycle is 1 minus the other 2 probabilities. And similarly, the probability of remaining in that progressive disease state is 1 minus the probability of dying within that cycle. Okay. Now, there's an exercise number 2, which will require your calculators once more, I'm afraid. Health economic evaluation is a very quantitative discipline, so there's no avoiding numbers. But if you can try and work through that one, and Andrew and I will come round and give you some assistance. So this is where we got the numbers. You've got these probabilities given to you. You've got 10% probability of progressing from the asymptomatic disease state, 30% probability of dying from that progressive disease state, and 10% probability of dying within a given cycle from the asymptomatic disease state. From those numbers, you can calculate the other probabilities, which are 0.8 and 0.7, with a 100% chance of you remaining in the death health state, obviously. And we can present that as a transition probability matrix. It's just a convenient way of presenting transitions. So your starting point is on the left-hand side. You could be in either the asymptomatic, progressed, or death state. And then there's a probability of you moving then to the column headings, which are your ending up state. Again, the asymptomatic, progressive, or death. And you can complete that table. And there are several zeros in that table, which indicate there's no reverse movement of people. So people can't become asymptomatic in this model from the state of the progressive disease. Obviously, a more sophisticated model could allow for that, and there may be some treatments that would be able to reverse the effects of this transition, and obviously we could model that accordingly. So you've calculated the probabilities, but what was the point of all that? Because all you've done in effect is to estimate the number of people in each health state for a given period of time. The purpose of all that is because we know, or we could estimate, a health utility, a QALY value, for each of those 3 health states. We can also attach a cost to each of those 3 health states. And because we know how many people are in each health state over time, if we multiply everything out, we can work out what the lifetime cost is for 100 people transiting between these 3 health states. So we can attach a utility and a cost to the health state. And we might anticipate a treatment to be hopefully effective, but it would be possibly, in this instance, effective in reducing the probability of one of the transition probabilities. So it might reduce the chance of death, or it might reduce the chance of disease progression. And what we would do is run the model with standard care, with these probabilities, and run the model with the drug probabilities, and compare the differences in QALYs and costs in order to estimate the incremental cost-effectiveness ratios you did previously. So this is what you did. You started off with 100 healthy patients, or green patients rather. I don't think they were particularly healthy, otherwise they wouldn't be prescribed the drug, but nevertheless they were in the asymptomatic disease state initially. We know that there is a probability that some of them will progress and some of them will die. I think 10% in each case. And so over the first cycle, you've got 10 in both those health states. Okay, that's all straightforward. 80, 10, 10. I think you've got the correct idea there. If you then go to the second cycle, the same probability exists you would multiply the remaining population in each health state by that same probability. And they would then move to the progressed and the death state, so that you have 64 now remaining in the asymptomatic disease state. 15 have moved to the progressed disease state, and 21 now have died. And you would continue that exercise. That just summarises the previous slide in words and numbers. And what's the point of doing this? Well, let's imagine that that this represents cancer, some form of a cancer and its treatment, and we would have clinical trial evidence over 12 months. So the vertical line at 12 months represents the evidence that you have from the clinical trial. So what in effect you have is survival curve, which is it's 1 minus that red line. Okay, so in survival curve, you've got everybody initially surviving and then falling over time. And what the red one plots is the number of people dying over time. So it's 1 minus survival. And that's the typical form of outputs that you might get from a clinical trial. But as I mentioned earlier, there's an issue of time horizon bias if we truncated the analysis at 12 months, because there'll still be a proportion of people who would receive treatments beyond 12 months, and people beyond 12 months will still accrue costs and QALYs. So we can't ignore those. And so what we do is fit a mathematical model, a statistical function, to the data that we have, and then make the assumption that that same statistical model would apply beyond 12 months. Because we don't have any other data to go on. It's a very strong assumption, but nevertheless it's a plausible assumption. We can test it, we can try different types of mathematical functions to see how they each perform, and hopefully they might all point to something which is comparable. So the data between 0 and 12 months is entirely from a clinical trial, which is just fitted using a mathematical expression. And the same expression is used then to simulate the data thereafter until effectively the whole cohort has died. And in numbers, this is what you have calculated. You did the first 2 cycles, and then I've just continued that all the way to 12 months, which is the trial evidence. So the trial would give you those probabilities. And then you would extend that beyond until, in this case, I've got 98% of people dying, obviously a few more cycles, then you'd effectively have everybody dying. And that gives you a distribution of where patients are over time in the model, with and without the treatment. This is perhaps the example without the treatment. Bless you. So for each of those health states, we can attach a utility value, a quality value, and a cost. And we have already said that the treatments might be expected to have an effect on one or more of these transition probabilities. And so we would recalculate it, assuming a different probability of transition. So the example that we have here is, this is exactly the same as what I've already presented. These are the probabilities and the number of people in each of those health states over time. I have assigned a cost. So if you are in the asymptomatic state, I've called it progression-free survival state here, it's attached with a cost of £400 per month and a quality value, a utility value of 0.8 on that scale of 0 to 1. In the more aggressive disease state, the progressed disease state, there's a higher cost in this example of £800 per cycle per month and a lower quality of life of 0.6. Okay, so they're just my made-up numbers, but they are the sort of things that you would anticipate in a health technology assessment. So then what you do is multiply out the number of people, the total in each of these health states. So over 23 cycles, so this is almost 2 years worth of projected data, there have been 497 patient months in the progression-free survival state, 164 patient months in the progressed disease state, and 1,738 patient months in the death state. We know that the utility in each of those states are 0.8 and 0.6. We'd multiply those out. And we know that the costs are 400 and 800, so we can multiply those out. And that gives you a total number of accumulated utilities and costs over the time horizon of the study. We need to make some adjustments because these are in months and we're interested in QALYs being over a year. So we need to divide by 12. But that would give you values of, there we are. So the expected number of QALYs would be 5 divided by 12. So you've got 0.42 QALYs in this example. So that's the number of accumulated QALYs in this patient cohort based on these transition probabilities. And the lifetime cost would be £3,300. Okay, so that, in that example, that would represent current standard of care. If we now had a treatment which has an additional cost, so the cost here is has gone up from 400 to, I think, 600, wasn't it? I think 400. Sorry, so it's gone from 400 to 800. So an additional £400 per month is the cost of this new treatment. But the treatment is effective, so the transition probability 1 has gone from 0.1 to 0.05. So there's a massive, 50% reduction in the risk of disease progression with this drug. And we would rerun the exercise that you did to calculate the movement of people between the health states and recalculate the total number of QALYs and the total costs over the 2-year period. And the answer would give you here 0.49 QALYs, so higher overall QALYs than without this drug, but a higher lifetime cost, £6,000 now, compared with 3,000 something pounds previously. We can then quite easily work out the cost-effectiveness ratio, which is the difference in costs divided by the difference in QALYs, and this example gives a value of £37,000 per QALY, and that would not deem to be cost-effective because it exceeds the threshold of £30,000 per QALY. There's one peculiarity here in the sense that this clearly is a very life-limiting disease. All people have died within 2 years, and the treatment has an impact on life expectancy. And it might be the case that this new drug would qualify under NICE's life-extending end-of-life criteria. which allows quite a lot of flexibility around the cost-effectiveness ratio, or the threshold rather, and increase it from £30,000 to £50,000 per QALY. And the idea there is that society values QALYs gained at the end of life higher than QALYs gained at other periods in life. Whether that's true or not is another thing, but that's the way that the NICE makes its decision. So based on a threshold of £50,000 per QALY, this drug might in actual fact be cost effective and would perhaps be approved by NICE. Right, this is how we might put that in an Excel spreadsheet. This has the code. I don't know if it's too small in your handouts or not. It's certainly too small for you to see on the screen, but it has the formula there if you were wanting to ever replicate or to look at this in more detail. There are some limitations to Markov modelling. It doesn't take into account any history. So people flow from one health state to the next without really knowing where they came from. So you can't model people's histories in a very straightforward way, although there are some ways around that, which I won't go into in any detail. The other thing we've assumed here is that the probabilities remain fixed. So regardless of whether you're on cycle number 1 or cycle number 20, your probability of progressing is exactly the same as 0.1. The reality is that that probability may change over time, and we can accommodate that simply by changing the probabilities for each of those cycles as you calculated them. So these are things that can be changed and adapted from the simple model. There is also some other further assumptions of it assuming a uniform population, an equal and constant risk over time. But there are ways around this, and there are different modelling approaches, and certainly I mentioned the discrete event simulation as one method, and that might be better suited in certain circumstances. Right, so the final section of this talk, just got 4 slides to go, is about uncertainty, because we've assumed here that everything is very precise. You will gain half a QALY, it will cost you £3,000. And obviously that's not the case, that's just the mean value. There's a tremendous amount of uncertainty around these estimates, particularly when you're extrapolating beyond available evidence. You have to factor in how uncertain you are. And in any clinical papers, if you weren't reporting the 95% confidence interval, then the reviewers will throw it back to you and get you to liaise with the statistician to be able to make proper scientific inference of the data that's been presented. And the same goes here. We need to take into consideration the uncertainty, not just in the clinical outcomes, but also the costs. There's tremendous variation in costs of managing people with all conditions. And there are different ways of exploring uncertainty, and these address different types of uncertainties. So for instance, there's variability between patients. So 2 people in our model, one might require 3 hospital appointments, whereas the other one only attended hospital once. So it'd be 3 times the cost, just comparing those 2 individuals. So we need to consider those differences and apply distributions to the data. There are parameter uncertainties from various sources, including treatment efficacy. I've just simply assumed the transition probability going from 0.1 to 0.05. Well, for some people, they will have no additional benefits. It'll be 0. For others, they may have, it'll go down to 0.01. And there's a distribution of effect, which are data that could come directly from a clinical trial on the benefits of treatment. There are certain subgroups who may respond better to treatment, and these subgroups could be identified beforehand, and we could look at cost effectiveness in different population groups. So it might be the case that certain patients, maybe with renal dysfunction, the treatment would be less effective or more toxic, and it would be far less cost effective in that subgroup of people. So there are various ways to explore cost effectiveness by different subgroups. And there are also this issue of model uncertainty. I've kind of taken one approach here for Markov, but I have said that there are many possible methods to tackle the same problem. And if I were to line up 5 health economists and everybody were to go away and do a model, I'm sure you'd get 5 different answers, and that's not to say that they're all wrong or they're all, that they differ because they've taken a different approach to the modelling. And we need to take that into consideration and look at the distribution of results based on 5 different modelling approaches. And there are ways to look at that as well. So simply, if we look at the testing parameter uncertainty. So let's say we weren't sure about the cost of treatment, or we weren't sure maybe about the utilities associated with treatment. Well, we can vary them. We could vary the cost, let's say, from plus £100 down to minus £100 either side of the central estimate. And if that had no impact on your cost-effectiveness ratio, then you could safely say, well, really, although I'm uncertain about cost, it's not impactful, so I'm not really going to be too fussed by that. However, if the cost is hugely influential on the cost-effectiveness ratio, to the extent that it might change the decision from something being cost-effective to not being cost-effective, then we would need to do some more work to find precise estimates of those costs. And one way to present all that is what we call a tornado plot, just because of the shape of these horizontal bars. And the example here, there's a cost of a particular treatment where it is clearly influential in the estimate of the cost effectiveness. So a small change in the cost of, I think it's lamotrigine in this instance of some work I did previously, had a big bearing on the incremental cost effectiveness ratio. The vertical line at the middle here would represent the base case, the mean incremental cost effectiveness ratio, and the either side would represent the change from that with different assumptions. We could also present this based on what we call a probabilistic sensitivity analysis. So we know that there's a distribution. It's not just changing one variable at a time. There's a distribution of costs, and there's a distribution of QALYs. And there's a correlation between costs and QALYs, just to confuse things even further. This is a plot, same as the one Andrew presented previously. It's a cost-effectiveness plane, where you're presenting differences in costs on the y-axis and differences in QALYs on the x-axis. There's a faint red X there, which is the mean point of the increases in costs and the increases in QALYs by that new treatment. And the slope to that point is the incremental cost-effectiveness ratio, as you did in the exercise earlier this morning. But that point represents just the mean. I could simulate my data 10,000 times. I would get 10,000 different individual estimates of cost-effectiveness, which are scattered all around that point. And that's what this cloud of dots represents. It's the result of each simulation sampling from distributions of QALYs and costs. The mean point is the same as you would calculate, as you did calculate earlier today, but then there's a probability, in fact, that the treatment is not cost effective because some dots are over here, way on the left-hand side, that cost more and generate fewer QALYs. So that for some patients, this treatment would be dominated by the comparator. There's a likelihood of that happening. There aren't any, in fact, that fall below the horizontal axis. And so, it's quite safe to say that this is a cost-incurring treatment. There's no savings in any individual patient being simulated here. But there's a reasonable chance of being to the left of the diagonal cost-effectiveness threshold line. So there is a reasonable probability of people, of this treatment rather, not being cost-effective. So while the mean would indicate that it's cost-effective, it's below the cost-effectiveness threshold, there's a likelihood still of it being non-cost-effective. So I've just shaded that in. So this shaded area represents if you counted all those dots and divided that number by 10,000, that gives you the probability of it being cost-effective at £20,000 per QALY. And with the blue shaded area would be the probability of it being cost-effective at the higher £30,000 per QALY. Okay? So it's not certain, there's no guarantee that this treatment is cost-effective at these limits of cost-effectiveness, because there are a whole number of dots on the left-hand side whereby that's not the case. We can present this in a slightly more user-friendly way, which is to calculate the proportion of points below the threshold for different values of the threshold. So if the threshold were £30,000, at this point here, we can safely say that about 88% probability of it being cost effective. If you had a lower threshold of £20,000, then there's a lower chance of it being cost effective, around about 80% chance of it being cost effective at that value. If I were prepared, or if society were prepared to pay £50,000 or more for a QALY, then there's a near 100% chance of it being cost effective. Okay? So this is called a cost effectiveness acceptability curve, and each NICE technology appraisal would have one of these as its main, or one of its principal results in terms of assessment of uncertainty. Now, you might ask, well, where does the significance come into play here? This is not significance testing. This is estimation. It's a different thing. This informs the issue of whether it's on balance, it's better to approve this medicine or not. So technically, if the probability of it being cost effectiveness is greater than a 50-50 chance, then it's better to adopt than not to adopt. So our threshold for adoption is much lower than the 95%. We don't need to be that certain in cost effectiveness for adoption, because it runs the risk that you'll deny access to a cost effective treatment. I think, Andrew, you've got some slides to sum up.
Just a short presentation to finish up then. So we've gone through all the quantitative aspects of health economics, but then ultimately we need to make a decision about whether to adopt the drug or not. Or the technology, I'm assuming it's a drug in this case. What I want to just briefly do firstly is to just recap who makes which decisions. So we've got three groups of bodies. We've got the regulators, which is the MHRA, and currently, maybe not for long, the European Medicines Agency. Thank you very much, Dyfrig. And they are making a decision about new technologies, but it differs from the decisions that we are making in the health technology arena. So they're making a decision about whether the treatment works compared to nothing, or usually as compared to placebo, and therefore assessing efficacy, safety, and quality of that technology in isolation. And this informs the decision, can we use it? In other words, will the drug or the technology be made available to the health service potentially to adopt? And then we've got the appraisal bodies that mostly consider the cost effectiveness side of things, which we've been talking about today. NICE, Scottish Medicines Consortium, the All Wales Medicines Strategy Group, and they are looking at a slightly different set of evidence, which is to inform the understanding of not does it work, but how well does it work, and not compared to nothing, but compared to the next best available option. And then in the context of how well does it work, does it represent value for money? And an important point to make on that is, of course, there are two sides to that equation. One is how much are we prepared to pay for it. The other is what price has been set. So we shouldn't forget that the pharmaceutical companies are setting the price against which we will judge cost effectiveness. And that informs the decision of should we use it. So the regulators decide should it be available to the health service as a whole. The appraisal bodies, the health technology appraisal bodies, decide should it be recommended for use within the health service. And then we've got the providers, which is in this country the NHS, and they deal with how is it going to be implemented and where are we going to find the money for it. So what we conspicuously haven't spoken about in this session is affordability. The assessment of cost effectiveness is not the same as affordability, but that's something that clearly the NHS has to consider as new treatments are recommended. So they consider how are we going to use it, and also how is it going to be paid for. So we're focusing on the appraisal bodies, and you've seen this lots of times. I won't go over it in detail, but clearly we've got the options that are dominated or dominant, which are no-brainers. We've got the ones in the other quadrants which require some judgment, and we set a threshold that informs our ability to make that judgment, and the gradient of that threshold gives a sense of whether we are prioritising effectiveness. If it was vertical, then our decision would be made solely on the basis of effectiveness, or cost. If it was horizontal, then our decision would be made solely on the basis of cost. The cost-effectiveness threshold, at least in principle, assumes that the health service has a fixed budget, and in principle, it represents the cost of the cost-effectiveness of the other activities that are being displaced by the adoption of the new technology. In other words, the opportunity cost. So as you recommend a new treatment, as we've heard about, something else has to get displaced in order to accommodate that new treatment. It may be within the same cohort of patients that something becomes unavailable, or more likely it may just be the health service as a whole has to absorb it. Perhaps they, in being less keen on employing locums to cover your shifts, for example, or not funding the rehab ward or something like that. It could be something quite distant. That's the principle, is that it represents the opportunity cost. An important thing to say, though, is that the NICE threshold of £20,000 to £30,000, I don't think really is explicitly based on an opportunity cost based on any empirical evidence. It was really, I think, set by some initial funding decisions that were made by the technology appraisal committees in the early phase of NICE, and it was felt that the £20,000 to £30,000 range represented the range at which the committees were generally accepting treatments to be cost effective. So this is a kind of graph that you will see presented in things talking about NICE and the likelihood of NICE recommending treatments. So the idea being that a treatment that comes in at a cost-effectiveness ratio of less than £20,000 per QALY is very likely to be accepted. Something that costs more than £30,000 per QALY is very unlikely to be recommended, and there is a range in between of increasing probability of rejection. My impression, I have to say, I think, and this is purely a personal impression, is I think that the curve looks something more like that, where there is a bit more of a cliff edge at £30,000. I think it's fair to say that as a committee you really have to justify quite strongly not accepting something that falls within the £20,000 to £30,000 range, but that's not quite the way that it's presented. Nonetheless, there is still some wriggle room, and it's important to consider what that wriggle room is for, at least in principle what it's for. And just briefly to run through these, probably a really key consideration, which we've just been hearing about, is the degree of uncertainty. So we will have the central estimate of what the cost per QALY is, but then, as you've just seen, you might have a probabilistic sensitivity analysis that shows that actually there's quite a high chance that that central estimate or rather that the estimate could, with a reasonable degree of probability, fall outside of the range of cost effectiveness. So we will consider the degree to which the parameters are uncertain, both clinical effectiveness and cost effectiveness. And this is just to give you the kind of idea, this is how it might look in a NICE appraisal. These, again, publicly available data. So this shows you how the cost per QALY can vary substantially. So in the case, this is for arenumab, episodic migraine, you've got costs per QALY, well, ranging from the treatment being dominated, that is to say that it's more costly but less effective, through to being highly cost effective at a cost per QALY of £3,000 or something like that, depending on which assumptions you believe hold true or need to consider. There may be some uncaptured benefits or uncaptured costs. So there may be some infrastructure costs or something like that aren't quantified. NICE is not supposed to take account of costs and benefits that fall outside of its base case unless specifically directed to do so by the Department of Health. But there may be some factors that you think, well, I've got the quantitative analysis, but there's something that it's not capturing that we need to factor in. And that may allow you to exercise some judgment about whether to recommend something or not. And then finally, we've got factors that are said by NICE to represent our societal preferences. And I think it's for you really to consider whether the degree to which you feel that these do reflect our societal preferences. They come from a citizens' council to some extent, so a kind of focus group, I think you could say. And I think it's also fair to say they probably filter down from some political pressure, but maybe the politics is again reflecting societal preferences. So as we've already heard, life extension at the end of life, so a quality that you gain at the end of your life, if you have short life expectancy, is valued higher than a quality that you gain during your life. And the weighting that is applied, just so you know, so the way this is operationalized is that if your life expectancy, the mean life expectancy is less than 2 years, and the treatment extends your life by more than 3 months, then the committees are allowed to weight the QALYs by up to a factor of 1.7, which effectively takes the threshold to £50,000 per QALY. The treatment might be innovative. It may have some benefits that, again, are not captured in the cost per QALY, but represent a benefit to society and to the health service that might be accounted. And NICE also has a duty to consider health inequalities. So it may be that the treatment, even if it's not the central estimate of cost effectiveness doesn't on its own support recommendation, it may have some benefit in reducing health inequalities that allow you to exercise flexibility in the decision making. These are the options, and again, this is a bit NICE-centric, I apologise for that, but just to present the options that are available to NICE committees and then the kind of outcomes. So what you will see is that the great majority of appraisals end in a positive recommendation, either for the original indication or for some optimised indication.
Can you describe an optimised indication?
I'm sorry, yes, an optimised indication is something that's narrower than the original marketing authorisation. So, for example, a migraine drug that is has a marketing authorisation for patients who experience, say, 4 migraines per month, but the committee might decide that it's only acceptable if the patient is experiencing greater than 15 migraines per month, that sort of thing. So it would be narrowing. NICE is not allowed to make recommendations outside of marketing authorisation unless specifically directed to do so. Okay, so that was all I wanted to say about that, but I'm very happy to take questions or points of discussion. I appreciate that we're slightly over our time. Thank you for your attention.